Okay, so we are recording. So I'll just make a short introduction and then I'll hand over to you, Carsten and Rudi. Okay.
Okay.
So hello everybody, welcome to the GCC June 2026 seminar. Today we are pleased to welcome our two speakers, Dr. Carsten Gerold and Mr. Rudi Rautenbach. So Rudi will make a short introduction and then Carsten will assume to present the rest of the session. So Carsten is a mineral processing engineer working for Loshi, and since 2019 he holds the position of senior manager for ore and mineral processing. And his expertise is in the fields of comminution and classification, dry and wet beneficiation of iron ores, base and precision metals, and phosphate rocks. And Rudi is the commercial leader in the mining equipment industry with plus 28 years of experience, spanning capital sales, project execution, and operations in Africa and Asia Pacific. And at Metso, Rudi now leads executive sales for Metso's HRC, HPGR, and also for the Metso Loshi VRM. So welcome to the GCC seminar, and feel free to share the screen and to start. It's over to you.
Thanks, Julian. Thanks for the introduction. My name is Rudi. I'm currently serving with Metso as the director for product support for HPGR and dry grinding. I'm based in Perth, Western Australia. I'm a metallurgist by background, originally from South Africa, and I've been with Outotec and with Metso, as you know, the two companies combined in 2021. I've been with them since 2012. So I'm joined here today with Carsten, who brings very deep technical expertise in VRM applications. And I think today's presentation timing is quite important. In February of this year, Metso and Loshi announced an exclusive partnership to bring the Metso Loshi vertical roller mill dry grinding technology into minerals processing applications. This partnership combines Metso's minerals processing flowsheet and service capabilities with Loshi's long-established vertical roller mill technology. And our objective with this was not to simply just introduce another grinding machine, but to really challenge how we think about comminution flow sheets in terms of how to simplify them, how to reduce the energy consumption, remove the need for grinding media, and support just in general more resource efficient minerals processing, things like steeper particle size distributions, improved liberation, reduced sulfide oxidation, and better flotation downstream performance. So in the session, Carsten will give a practical overview of the key features of the technology and what potential benefits it may offer over more conventional grinding circuits. So with this, I hand over to Carsten. Thank you.
Thanks very much, Rudi. I think one point to mention here as being important is that Metso now has always had the capability to test different technologies. We will not really go in depth into that, but in principle, this is also the case here. So if Metso for a project chooses the vertical roller milling technology, each other technology available has also been tested and compared, and so that the final outcome is then really that for this given project, the VRM is the preferential case. And now I would like to guide you a little through vertical roller mill for ore grinding. What are the key features and benefits? And some of you I know the technology very well, others don't really, so I try to squeeze in as much as possible within these 45-50 minutes. There might be some points open, but then kindly just raise your questions afterwards, and therefore let's start. So vertical roller milling technology is not a new technology. In 1927, the grandfather or momentary owners invented this technology. And the start of the company or vertical roller mills was in 1927. The company itself is a little older, from 1906. But then we introduced this technology into a new market, which was raw material or raw mills grinding, which is basically limestone grinding in the cement industry. Afterwards, Löscher was the first to introduce this technology to the cement and slag grinding. And additional to that, to industrial minerals. And since a longer time, we also have a few applications in ore grinding. And the latest one is the West Musgrave project, where we have been awarded for a 12 million ton copper nickel grinding plant in Australia. So this is not a new technology. It might be new for the ore industry, and surely we see regional knowledge differences. For example, in Australia, a lot of people are now familiar with that. In South America, it increases. In South Africa, also some more people know about it. But together with Metso, we are very positive that we can now spread this technology much deeper into the industry. Okay, let's talk about the functionality and the flow sheets. So on the left-hand side, you see a grinding plant, and it's actually crushing and grinding. The VRM or vertical roller mill is kindly misleading because it's really crushing and grinding. And the advantages we see that depending on the circuits we utilize, we can provide energy savings up to 40%. It's a dry grinding technology, therefore it enables fully dry or reduced water processes. We don't have the need for grinding media. It's a very compact design that can be achieved, so comparable to the footprint of an SABC circuit, but with reduced civil and steel works. The technology has an outstanding reduction ratio of 3,000, or actually even much higher than that. We can theoretically feed 150 millimeter and grind them down to a P80 of 20 micron, mainly by an internal grinding classifying circuit. What we see through the compressive grinding that we do is that we get an improved mineral liberation, less sulfide oxidation, steeper particle size distributions, improved downstream recovery, and up to 7% better flotation performance. Up to now, we installed more than 2,400 VRMs. And there's different points we will touch today. So there's the columns of operating expenses. We just mentioned up to 40% energy savings. We have few stages of reduction, no grinding media. The water saving potential is up to 25%. We will get examples for that. It can also go higher. And grinding media saving is also a big point. It's up to 97% lower metallic impurities. Other points that we will touch is the downstream behavior, like the steeper particle size distribution curves we get with up to 20% less fines, minus 20 micron. We see a superior mineral liberation rather than size reduction. And like already stated, up to 7% better flotation performance. The particle size distribution we get out of the machine, because it's pretty steep, also improves the recovery and magnetic separation or density separation. And the point which I think is really important for the ore industry and very beneficial is the operational flexibility, because the technology can adapt to feed changes within minutes. It offers stable production and product quality because all the main grinding process parameters are online controllable. And having a dry grinding product, you can buffer between the comminution and beneficiation process, which can be very helpful in different occasions. But now let's touch the OpEx aspects a little bit more. Firstly, a general flow sheet, or a standard flow sheet, how I would call it, is we have the primary crushing coming from the left, secondary crushing, and then we feed the Metso Löscher VRM. At the end of the process, we have a fan. That fan is sucking air through the complete system. I'd like to recall it's a dry grinding principle. And the final product is dedusted in a baghouse. And usually the target is to produce a primary feed for primary flotation, for fine leaching, or for the rougher magnetic separation. We will talk a little about the way how the mills are built up. The comminution area, comminution zone with the grinding table and the grinding rollers, in our case conical. The grinding happens, or crushing grinding happens in a compressive bed, and through the conical rollers we combine compressive and shear forces, which brings us a pretty good degree of liberation. And like said, having a dry grind product, we can buffer between comminution and the beneficiation processes. The reduction ratio of these machines is really astonishing, and therefore processes can be much simpler with increased efficiency in comparison to other technologies. You all know the rates mentioned above, but in the Löscher mill, you can feed 150 millimeter and grind it down to 20 micron, which actually is about 7,000, but we didn't want to go that high in the numbers. But taking the picture on the right-hand side, you see all the different comminution equipment for the given particle sizes. And the VRMs have an outstanding reduction ratio. And you see within that red square, basically, you can start feeding the mill with any of the given sizes. So you can either feed it very coarse, if you have a soft material, but you can also feed it with 150 micron if you want to grind iron or concentrate for pelletizing, for iron pelletizing. So it's a really flexible piece of equipment. The way it's built up, remember, we are in negative pressure, so we need an air sealing system, which is achieved by that feeding bin. We have an apron feeder, could also be a cross belt. From there, we feed the material onto the center of the grinding table via the feed chute. The mill table is driven by the mill gearbox and the mill motor, and then we have the grinding rollers, which are fixed. And the comminution zone is between the fixed grinding rollers and the turning table. In the bottom, you see the gas inlets. So the fan is sucking air through the mill, through the baghouse, and then, if you like, you can recirculate it. But the bottom part has the job to equalize the gas flow, and then the gas evenly streams into what we call the process room or process area. The grid cone has two jobs. On the one hand, it optimizes the gas flow to the classifier. It's a high efficiency dynamic classifier, which you see on top. In the same time, everything that the classifier rejects is guided back to the center of the grinding table, where it's recombined with a fresh feed. So we mainly have an internal grinding classifying circuit. There's just a little portion of about 10% that is then discharged via that conveyors here in the bottom and mechanically transported, because we don't want to apply that high energy to also keep these big particles in the mill. The classifier, like I said, is a fourth generation dynamic classifier. And then the product gas stream goes to the baghouse. This is how the mills look from the inside. This mill is a 69.6. That means 69 decimeters, so 6 meter 90 table diameter and 6 grinding rollers. The height up to here is about 35 meters, so it's a big piece of equipment that we talk about. Because the classification is completely different to what you usually know in cyclones or screens, I think it's worth to touch the classifier itself a little bit. The classifier consists out of the guide vanes, which are static. You see them here on the outside. Then we have the rotor, which is the internal part. The rotor is turning. The rotor blades are the vertical blades that we can see here. And the rotor is driven by a motor in the gearbox. The advantage of the classifier is that it really streamlines material flows in the circuit. It eliminates ductwork between comminution and classification. It eliminates dust leakage, so it's really good because a lot of people are concerned regarding dust emissions, but because everything is a negative pressure, you don't have to fear about that. The classifier prevents from material circulation. It reduces fan power, and therefore it cuts energy consumption. It reduces material handling and eliminates the need for air slide conveyors or bucket elevators, which lowers your maintenance requirements. So what is the difference now with a Metso-Löscher VRM for ore grinding? The point is there's a lot of VRMs on the market, but we really took a lot of time and research and optimization work to make it suitable for the mining industry. Because within the mining industry, you at least have to achieve an availability of 91% or 8,000 operating hours. We can extend that even by using the dry product silos for buffering. We have a lot of innovative concepts to speed up and ease up maintenance because that's important to get the acceptance in the industry. And we utilize high quality wear parts which are optimized for easy and safe exchange. In general, all parts that are exposed to impact or jet wear are protected, and everything that is facing impact is protected by hard-faced liners, and areas where we have jet wear are protected by ceramic liners. So taking a look at the different occasions of wear, the red circuit areas are the ones where we have impact, which is in the feeding areas, but mainly when these particles up to 150 millimeters bounce on the table or turning around, thrown around. So these are impact areas, while the jet wear is happening wherever you have the particle transport, which is inside the mill in the internal grinding classifying circuit, or when the particles are fine enough and they go to then the baghouse. Therefore, we choose different wear particle or wear products for the different areas of the circuit. And that makes it basically unique in the industry. Another equipment that is pretty new to you probably is the way we de-dust the systems. In this case, the example of a Scheuch baghouse, because somehow we have to get the solids out of the gas flow, and that is done in these baghouses. Simplified scheme in the bottom here. So raw gas, which is gas that is loaded with solids, is sucked through the baghouse. On the right-hand side, you see here this empty chamber in gray. And from there in the bottom, you go to the left and right baghouse compartments where you see in white the filter cloth. So the material is basically following the gas flow and therefore is finally sucked onto the bags where it builds a filter cake. So you can imagine material accumulates on the outside of these filter cloth, and therefore it's getting more difficult to suck the air through, which you can measure by a change in the pressure drop. And then there's an automated cleaning device that then cleans the bags. So this is the way how we can de-dust the material out of the gas stream. The dust emissions in modern baghouses are below 10 milligram per cubic meters. If it should be required, we can also reduce that to 5 milligram. Let's talk a little bit about the plant layouts. On the right-hand side, you have to imagine that there's the secondary crusher pile. And then we have a tramp metal removal, the feeding to the mill via the feed bin, apparent feeder, we have the mill. At the end of the process, we have the fan. In the middle, we have the baghouse. So the air circulates basically within the circuit if needed. And then we have the reject recycle, which is the coarse fraction that I mentioned before. So that is mechanically transported. But as there could also be some tramp metal, we also clean that one from tramp metal. And now I would like to show you a short movie because it touches a lot of the points that are mentioned here. Just making a short stop here because I think, especially for comminution people, this is the interesting part. So the material is fed to the center of the grinding table, and then via the speed of the table distributed to the outside below the roller. Circumferencing the grinding table on the right-hand side here to be seen is what we call the dam ring. We utilize the height of the dam ring to adjust the product particle size, respectively the retention time. And surrounding the grinding table is what we call the louver ring. This is where the gas enters the system. And just that you understand where now what is happening in the comminution zone is between the grinding roller and the grinding table. Okay, so now let's talk a little bit about how the VRM increases the efficiency of the mining industry. Coming back to that slide with all the benefits, we now want to touch a little bit on the downstream behaviors. And therefore, it's important to understand how the comminution or rock crushing grinding really happens, because we have a bad breakage. So let's say this is between 60 to 120 millimeters, depending on the mill size and the final product particle size, but you will always have multiple layers. So the particle happens in multiple layers. It's a combination of compressive and shear forces, which act simultaneous on the particles. We have this fluid-like stressing from all sides on the agglomerates, and therefore we see preferential crack initiation at the weakest point of the structure, which is typically along the mineral grain boundaries. Resulting microcrack formation enhances liberation while reducing excessive fines generation. It's an enhanced intergranular breakage that leads to an improved degree of mineral liberation, and we see increased selectivity due to the preferential breakage of the mechanical weaker mineral. To add that, I forgot to mention that, because usually you don't have that much control over your grinding forces. Within the VRM, you have the hydropneumatic spring system where you can steplessly control your grinding forces and thereby really optimize them for the purpose. And the result of this, the way we grind, within the movie, you saw that after being ground, the material is accelerated and then gets the chance to be classified. So with this very quickly internal grinding classifying circuit, after 1 or 2 grinding contacts, we classify the material. So we take it out as soon as it's fine enough and according to the specification. And that results in a completely different product particle size. This is the example of a joint work we did with Anglo American on a UG2 platinum ore. The bond work index is around 24. And what is compared here is in green the product particle size of a lesser VRM in comparison to ball milling. And the black curve is the industrial ball mill, the gray one is the laboratory. And what you can see is we have a steeper particle size distribution in total. We have less fines in here, and we have less coarse. And that's changing your degree of liberation very much, because you can imagine in that coarse area here, there's still intergrowths between your valuable minerals and the gang material. But with that direct classifying we have, we get a very efficient classification, so a steep classification. And therefore, these product particle size distributions look different. And if it's steeper, it's easier to adjust your downstream process. So every particle gets the treatment it requires. And in comparing the VRM system to other systems, in this case, that was done with Anglo American research on a zinc ore, and an hexagonal ball mill circuit were compared with a crusher HPGR ball mill circuit, cone crusher vertical roller mill, and cone crusher HPGR vertical roller mill. And the most energy efficient was the combination of cone crusher and vertical roller mill. There will be processes where it's very beneficial to combine an HPGR with a vertical roller mill. But in this case, because it was a zinc ore, it didn't really make sense. But the energy saving here that was achieved was above 31%. Here's an example of a Chilean copper ore that we ground to a P80 of 212 micron. And as it's a dry grinding technology, you can easily imagine that the galvanic interactions that you face when you have wet grinding, with all the high grinding media consumption in the ball mill, the galvanic interactions are having a strong effect on your flotation performance. And the fresh created dry surfaces, they respond very good in kinetics and flotation kinetics. And copper floats very well anyway, but even here we could increase the copper recovery about 1.3%, and the molybdenium for about 6.5. And that is to be explainable. Molybdenium is a very soft ore or soft metal. And usually in the ball mill, it often tends to be overground and then it starts to smear. But because we directly classify it out, we could highly increase the molybdenium recovery. So this is a thing that we often see, depending on the element, sometimes stronger, sometimes weaker, but we often see improved flotation performance. Speaking about grinding media consumption, in this case, it's a plan where lesser VRM is operated in parallel to a rod mill ball mill plant with a tertiary crusher in advance. And here we utilize what is high chrome grinding elements. You see on the top right, the grinding tire, in the bottom right, it's the grinding track. And high chrome is the, let's say, lowest quality that we use. But in this case, it's a phosphate rock. It has a bond work index of 24 kilowatt hours per ton. The comparison of wear is that 143 gram specific grinding media consumption is achieved with a rod and ball mill, and the VRM has about 4.31 gram per ton, so massively lower. And that's about a 97% reduction. And that surely is very positive for flotation because you have less metal in flotation, but you also have a 40% cost saving. And if you consider the metal and the production of the metal, it's also significant CO2 savings. So let's talk a little bit about references and case studies. The first one I want to speak about is the West Musgrave Copper Nickel project. It's ore with a bond work index of 18.4. The A-type speed is 37.3. And yeah, you can see the other data there. So initially, they were targeting to work with a SAG mill ball mill flow sheet with pebble crushing and sequential flotation. But yeah, that was because this plant is in the middle of nowhere. It's 600 kilometers away from the next electrical grid, 800 from the next city, so there is really nothing. And they were looking for ways to optimize the project efficiency. And we carried out a lot of pilot test work together with them, and finally they then changed the process in the pre-feasibility stage to primary crushing, secondary crushing, and then VRM for grinding, followed by bulk flotation and regrinding. And taking a look at the grinding advantage, in this case, we had, let's say, only 20% reduction. But considering that this mill is really so far off anything, the cost saving for providing the energy is massive. It was one of the first hybrid projects. The target was to go with solar power, wind power, and accumulators to basically run the complete project. And this is also one of the reasons to decide for the VRM, because to utilize renewable energies, you need a flexible grinding system. And that is very difficult with a wet tumbling mill to achieve. But the vertical roller mill, we will come to that, as all the main process parameters are online controllable, can be easily adjusted to the conditions that you have. But it was not only energy. Different flotation programs have been carried out. And in this one, the nickel recovery was 2% higher, copper recovery was 0.5% higher, but they also optimized the flotation device a little bit, and then up to 4% increased nickel recovery could be seen. The copper recovery is more or less similar, so it always depends a little bit how you tune your flotation device, but nickel really responds very nicely to be ground dry, and we saw that in a lot of other projects too. So when we take a look at the plant layout that was chosen, you see that it's two plants, one behind the other. The feed is coming from the right-hand side. And at the end of the process, the product is buffered in 3 product silos. So they have a 12 million ton per hour annum production with 1,500 tons per hour capacity in the grinding and in the flotation. And with these bins, we can offer a continuous operation of the flotation circuit during maintenance. Just because you take out one of the plants, but the other plant can operate with a slightly increased throughput, and then you still have these 18,000 tons of silo, which are just possible because it's a dry grinding product. And then you can do maintenance on the plant, and when the maintenance is over, you just switch back the plant, and then you're back to production. And to show you what happens it depends on how much you want to reduce your flotation. The normal case would be 1,500 tons. But if you reduce it basically to 1,000 tons, so you reduce the capacity in flotation by 33%, you could basically run maintenance for a very long time. But this is a thing where I really see a benefit in dry processing or dry grinding. Now let's come to some other circuits. What I showed before is what we call the airflow circuit. The case I want to speak about now is the southbound case. That was a bankable feasibility study with Grant Resources and Wood for a project in Western Australia. Initially, the flow sheet looks similar, but what is different is we take the coarse fraction of the classifier, guide it to a magnetic separator, and we just recirculate the concentrates, while we try to separate the non-max, the gangue material, as early as possible. In the same time, or the main idea is to produce a product for dry magnetic separation and flotation, but surely we want to reduce the amount that have to be ground. And by that process, we have an early waste rejection. We have a reduced amount of ore to be ground, because you can imagine all the silicious fraction that we take out is increasing the capacity, it's reducing grinding media consumption, and also lowering the energy. And we just lately received the patent for this process, and therefore, yeah, we really think it has a lot of potential. And additional to just reducing the mass to be ground and optimizing the process, where it's getting really interesting, because this size fraction is about P80 250 to 550 micron. So you can do very nice things with that. Originally, within that project, all the gang would have gone to a tailings pond. But within that project, because we could separate about 35% of this dry coarse fraction, that can be commingled with your fines from the other processes. So basically, just by changing the process, you suddenly can switch to dry stacking. And regarding the permit structure in a lot of ore projects, that's a real benefit. So giving some more numbers from the pilot campaigns that led to the project. So within the pilot test work, we even achieved higher rougher magnetic separation rejection of 41%, but for basically the business case, that was reduced just to be more on the conservative side. But the magnetite enrichment that could be achieved simply in the grinding, you could increase the magnetite from 35 to 56% as part of the grinding. And that really simplifies your process, and it highly extends your dry processing. Comparing now the final data of the solution that the Metso-Löscher VRM provides in comparison to the wet milling, which was an SABC circuit, wet SABC circuit, which resulted in 20.8 kilowatt hours per ton. We had a 41% saving of energy. We could increase the gang material that was rejected by 9%, and the plant water consumption could be reduced from 5.1 gigaliters to 3.9 gigaliters, which is 25%. But one of the biggest issues, like just said, is changing, or to be able to change from wet to dry stacking. The saving in energy equals 127,500 megawatt hours per year. In water, it's 1.2 gigaliters per year. And to visualize that a little bit, 127,000 megawatt hours is about the energy consumption of 9,100 average households in the EU. And when you consider the water amount, that's about 1.3 Olympic swimming pools per day on water that you save. And surely for areas like Australia, Chile, Peru, Southern Africa, Northern Africa, where water is critical, this can have a massive impact on your project economics. And also in getting it running at all. For that new process, we received a high commendation from the SIG, which we are really happy about it. And they saw that this work will have a significant impact on the industry. And therefore, we also got a nice certificate, and we're really happy. Another thing which we think where the VRM is very valuable and could easily be installed in processes is pebble grinding. Because pebbles often are difficult to foresee what happens, that they suddenly arise, and so they disturb your circuit, they accumulate, and the circuit's getting less efficient. But what would be if you can take out the harder to grind pebbles? Just send them through the VRM, and within the VRM you can bypass the complete system, because the VRM can do the same job as the SAG mill and the ball mills. So you basically have a primary feed for your flotation process, and then you can decide if your pebbles are different in mineralogy. You might even choose a different flotation circuit. Other than that, you can just combine it with a product of the wet process. And wet processes always have the issue that they are not constant in feed. So that will even be an ideal solution, because if you have fluctuations in your wet circuit, you can easily stabilize the feed to flotation with that dry product, because you can dose it exactly the way you need it. And by taking out that harder to grind component, you take it out of the complete circuit, therefore your sack capacities increase over proportionally. And in the same time, you feed less hard minerals to the ball mills. So also the ball mills benefit over proportionally in capacity. So we think this is really a nice thing for VRM applications. An important point, and that's a big difference to conventional tumbling milling, for example, is the operational flexibility. Because we will talk about why you can adapt it to feed changes within minutes and how we can stabilize the production and the product quality. And the main reason is that all product parameters are online controllable. And next to that, the buffering, but that's not really process related. But let's talk about the process itself. Speaking about the mill, we can precisely adjust the feed amount to the mill. We then have the grinding pressure, which together with the table speed defines how efficiently the comminution is happening. So that is one of the force pairs that we have. The other thing, the volume flow, which these blue arrows to the top, you can imagine you have a suction to the inside of the classifier. So this is one force. The other force is the centrifugal force created by the classifier RPM. The faster the classifier turns, the higher the centrifugal force to the outside. So therefore, in a normal operation, when you just change the classifier RPM, you also change your product particle size. You can basically follow your degree of mineral liberation, which you will never, or very difficult to achieve that with a wet milling system, because you have your ball charging and you're relatively limited in the range that you can set up for your critical speeds. But in this technology, it's really very easy to change your final product or follow the degree of mineral liberation. What we see as really big advantage is the differential pressure that we measure. Within commissioning the plant, we measure the differential pressure, which is nothing else than a signal for the internal circulation we have in the mill. And you can identify when this is at an optimum point. And then when you see, let's assume the case that your feed is getting softer, what would happen? It would grind faster, so it would leave the circuit faster. In the same time, you then see, okay, my pressure drop is reducing, which means the mill has capacities left. And then you can just automize your feed to stabilize that pressure drop, which means nothing else than feeding more material to the mill, and therefore utilizing the mill to the maximum. The alternative is that if the ore is getting harder, it would accumulate, so your pressure drop would increase. So there's different ways. One is just to reduce the feed, but usually we would foresee some pressure reserves within it's a hydraulic piston die system that basically pulls down your grinding rollers to the table. Therefore, by increasing the grinding forces, you will get more efficient grinding or more efficient comminution. And then you can even stabilize your throughput, although your ore is getting harder. So this is a really very flexible system. If you have to dry, for example, for gold roasting or nickel roasting processes, we observe the temperature to ensure that we don't utilize more than necessary heat and therefore fuel and costs. And we also measure the product particle size. And with the product particle size, we can use that signal to automize the control of the classifier RPM. And hence, if we see that your product is going out of spec, the system can control itself automatically. And therefore, we would summarize it as that the Metzer-Löscher VRM online control is a superior process control and hence superior plant efficiency and product quality. You can adjust the mill to changing feed characteristics within minutes. The ramp-up time is about 10 minutes. And that is, I didn't mention that, but the particles are really very shortly in the Löscher mill. And the normal process if you take a tumbling mill, you have to wait until your material really leaves the mill. And although it might be already ground to spec, it will still have to stay for another 10 minutes, 15 minutes until it's ground to, or until it's leaving the mill. And that can add chipping, so you increase the amount of fines. This is also one of the reasons why the product particle size distribution is coarser. And it's ready for renewables. We touched on that because it's so flexible. You can utilize that if you have less power available, for example, because you have a cloud bench. All you got to do is set your feeding parameters, adjust your pressure, grinding pressure accordingly, change your classifier, and you can work with the existing amount of energy always in an optimum range. So you don't have to shut down the mill, but you could even do so. In the project I reported, the West Musgrave, the 2 lines, the idea would be if the power drops too far, you just stop one of the lines, because you can shut it down and then switch it on as you like. It's not like in a wet circuit where this is very difficult because you would have to flush, and where it also takes about half a day to stabilize. So these systems are really quick and flexible. Speaking about test capabilities, we have at the moment 2 places where we can test the vertical roller mill. It's going to be more, but at the moment there's the Leisure Test Center in Neuss, and we have a mobile unit which is called the OGP Mobile. You see here on the right hand side, and up to now we tested ores from a lot of areas in the world. In total it's 238, the majority of them being iron ores, followed by copper ores, phosphates, respectively gold, phosphate, a lot of others, nickel, tin, zinc, manganese. So we gained quite a lot of experience over how this technology behaves or to different ore characteristics. In general, we can say if the ore is getting harder, the efficiency of the VRM is getting harder or is getting higher, because tougher ores are more responsive to the compression forces, and they are more brittle. So there we see a much bigger difference than to tumbling mills. And the way we design our mills or scale up our mills is under continuous cross-check. We have 120 years of experience in comminution. We have 2,400 mills that we sold. We permanently do research. We have more than 11,000 grinding tests that we carried out, 22,000 industrial data sets, and we tested 238 ores. And all this is permanently, let's say, put together and check that the scale-up procedure is solid. So that was what I wanted to show you. I hope that's was a lot, but everything just touched a little bit. But therefore, we might have time for a few questions.
Thank you, Carsten, for the very nice talk. Thank you, Rudi, for the talk too. So we have time for questions. So if you have it, just open the mic and speak up.
So then perhaps I'm coming as an icebreaker here. Thanks a lot for the nice talk, Carsten, for the interesting information. Typically with the millers you presented, the issue is that they work well for dry ores, and quite often you find quite moist ores in the mines. And so drying costs energy. So how about moist ores? What do you do? How are you addressing moist ores?
I mean, that is surely a limiting factor. The point is, if you, for example, have to go for a gold roasting or a nickel roasting, you will find nothing more efficient, because we have basically fluidized bed inside the mill. Therefore, the drying is about 20 to 25% more efficient than in a normal drum dryer. But you're fully right. If you would have an underground ore with 50% moisture, then this is probably not the technology if you don't want to go for a dry first sorting step. And therefore, we then choose where the mills are well suitable. So I would say up to 5% moisture, we are always OPEX positive, and then it depends a little bit on the ore characteristic. It might go up to 8% moisture where you still get the OPEX positive. But additionally, you have the benefits that you still have the increased degree of mineral liberation, the steeper particle size distribution, the footprint, the flexibility. So these topics are additionally still coming. But moisture is a limitation, you're right.
Thanks.
That's all. Hakan.
Thank you, Carsten. Very interesting presentation. I would like to ask a question regarding the damping height. So, is the capacity directly affected from the damping height, or just the damping height affects only the product size?
No, surely you have the damping definitely affects, on the one hand, your throughput, because let's say iron ore grinding is a good example. If you want to grind for just feeding a rougher magnetic separation, you would set up a different height than you would if you go for iron ore concentrate grinding for pelletizing. Because pelletizing, you are targeting plane, so surface, while for iron ore, you are targeting for mineral liberation. And you would choose a higher damping for the pelletizing process to keep the material longer on the table to increase the surface, but that comes for the cost of higher energy and surely in consequence also lower throughput. So you could increase the throughput if you just say I go for a residue, let's say 20 P80 45 micron, then you would get a 10 to 15% higher throughput out of the mill, and probably also much or even a bigger saving on the energy side.
Thank you, Carsten.
I think Ben.
Hey, Carsten. Yeah, thanks for the presentation. I had a question about wear and abrasivity. So what's sort of the hardest or the most abrasive ore that you've tested in the VRM, and how do you go about estimating the wear rates and the maintenance schedules for those type of pretty abrasive ores?
Let me see if I, by chance, have a slide. Because hardness,
by the way, a very good question.
No, but we tested basically everything. We tested the Gaita ore, which, if you know this A times B curve with Yanacocha Gaita, so we tested up to 29 A times B values, and yeah, we never saw a thing that we cannot grind. If it's the UG2 platinum, Platreef platinum, so like I said, if the ores are getting harder, they're getting more responsive. Tackling the wear issue, we would then probably decide not to go for the maximum feed capacity we can feed to the mill, because as a rule of thumb, we say the feed size is about 5% of the mean roller diameter. So for a 3-meter roller diameter, you could feed 150 millimeter. If we would get a extremely tough feed size, we would reduce that feed size just to reduce the wear. But then we can nicely cope with it because, it's still a grinding bed, so you can then control the wear. And the mill is built in a way that everything is maintenance easy, maintenance friendly. And that's a big thing that we changed in comparison to conventional VRMs. So this is where the major difference comes from our mill to, let's say, normal VRMs, because we had a few installations where we faced wear. They were built like cement plants. And so we had a steep learning curve to see that there is definitely differences in the abrasivity that you face in the ore industry in comparison to the cement industry. And we responded by smart ways to speed up the maintenance. We can easily talk about that in a separate meeting. And after we ground your ores, we do that. And while we really put a lot of effort in achieving comparable availabilities to what is expected in the mining industry.
And Carsten,
Marcelo?
you've also developed a specific proprietary test to determine abrasivity and then scale up the estimated wear life from that testing. Yeah.
Yeah, a point that we usually mention within presentations like that, because when you want to scale up a Le Chauvier M or Metso Le Chauvier M, we always do pilot work. So within that pilot work, we have a grinding test. Within that grinding test, we know how much material we have ground under which conditions, and we can measure the wear of the grinding elements. And then we have, for industrial applications, we have higher qualities that we install. And this factor, we then can apply a factor to predict the lifetime of the industrial application. But surely this is based on pilot test work and knowledge of the material properties.
Okay, cool, thanks.
Right, Marcelo?
Yes, I enjoyed seeing the presentation and having the news of the partnership and as well knowing about this pilot work and the prospect of applications in Australia. Fantastic. My question is also along this line, but very specific along the lines of wear, because you mentioned of using high chromium tires as one case for phosphate. And I was wondering that some time ago you mentioned about the possibility of using studs in the rollers. Can you just talk about that if you're further considering, or you really forgot about that possibility of following pretty much like HPGRs do with the tungsten carbide inserts?
I mean, the example I showed is one specific mine, and they utilize that basically lowest quality that we have. And surely there's much better quality is available, and studs could be one of them. So let's see where our work is carrying us, and invite us in a year's time and we will tell you more.
Okay, thanks.
Malcolm?
Good to hear from you, Carsten and Rudi. Can't miss your accent, Rudi. I'll ask you a slightly sideways question. I've got a whole list to ask you, but I'll ask you just one. Is you do a lot of magnetite, but you want to have tramp protection up front, and there's the direct problem of removing steel with magnetite. So I wondered whether you can use standard magnets and what size steel you need to remove. So what's the largest you can bear in the machine without damaging the rolls? So
we are extremely conservative on that regard. We usually say it's an M8 nut. This is critical, that's true, but this is like a general rule. I mean, with a high grinding bed, we don't necessarily do that or need to do that. That comes more from the cement industry. But the other question, when we do magnetite projects, we don't have a tramp metal magnet. We solve that issue via the metal detector. And then you can basically, if you have a steady stream, it's like a ground noise. And just if you then get a peak, and that peak will be your signal that there's a solid component of tramp metal in there. And then you separate that out of the noise, basically. Mm-hmm. So there's solutions, Areas provide solutions. Wagner provides solutions for that, which are also industrially proven.
So what bed depth do you typically run at then?
Let's say the metal detector is in the feeding belt. So we have to ensure that we enable the metal within the feeding belt. We have a metal detector, and then there's a Y chute, and the Y chute separates out metallic particles prior to entering the circuit. So let me surely take the chance.
I mean, actual bed depth under the rolls.
So the bed depth under the rolls is usually should be for magnetite projects in the range of 80 to 120 millimeters, depending on how coarse you go. But the tram metal removal here on the right-hand side, this is when you come from the secondary crusher. It's just basically a metal detector. That metal detector controls a two-way chute, and then you can get the tram metal into this. It's a metal bin. We call it a metal bin. We utilize the same for the reject. And then with a slow running belt, we have another metal detector to get rid of the tram metal, but to keep the ore within the circuit. So this is well-proven systems that we utilize in the cement industry since decades.
No, so it's a two-stage. That looks pretty good. Yeah.
And you have a 2-second flap. So your Y chute turns out for 2 seconds, and then, yeah, basically, this is why we like to work with that bin, because then we can really recover all the ore and just get rid of the metal particles. Some clients, they might, for cost reasons, decide, okay, we don't need that bin, and they just live with a little bit more material, which they then just deposit in the mine.
I think it's also a function of throughput. If you've got several thousand tons per hour, just a second or two means a massive materials handling problem down the line. So if it's a small mill, yeah, maybe you can get away with dumping it. But for the larger mills, I'd say it's almost mandatory to have that proper rehandling circuit.
No, that's interesting, because I was wondering how you get it down. You two-stage it. That's very good. Yeah. Thank you.
We can set up a session, Malcolm, if you have a lot more questions, we can set up a separate one if you like. Always good to have interesting questions.
All right, so let's thank you again, Carsten and Rudi, for the very nice presentations. And thank you all for attending. We have a break now in July, and we'll be back in August with another seminar. So thank you all for joining, and see you there.
Cool.
Thanks for the opportunity.
Again.
Thanks, Thanks, Errol. Thanks, Rudi. Yes.
Okay.
Bye,
Thanks, guys.
Excellent.
Bye.